Right now, as you sit there, space itself is moving faster than light. Scientists have made light crawl at bicycle speed, then stopped it completely. They've created light that arrives before it leaves, and in every swimming pool on Earth, particles are breaking the cosmic speed limit and creating tiny light explosions. Everything you think you know about the speed of light, it's about to get flipped upside down. Okay, let's start with what everyone learns in school, the speed of light. 299,792,458 meters per second in a vacuum. Nothing can go faster. Einstein proved it. Case closed, right? Wrong. Most explanations skip this crucial detail. When physicists say the speed of light, they mean something very specific. They're talking about light traveling through perfect empty space, a vacuum. That number, which we call c, isn't really the speed of light. It's the speed limit of the universe itself. Here's what's wild. Light doesn't always travel at the speed of light. Think about it. When light goes underwater, it slows down to about 225 million meters per second. Through glass, even slower. This isn't some weird exception. This is completely normal. Light has to interact with all those atoms and electrons in the material, and that slows it down. It's like trying to run through a crowded hallway versus sprinting across an empty field. But what if I told you scientists have slowed light down so much that you could literally jog past it, and that's just the beginning? In 1999, physicist Lena Howe at Harvard did something that sounds like magic. She slowed a beam of light down to 17 meters per second. That's slower than you drive through a school zone. Later, she did something even more incredible. She stopped light dead in its tracks. Here's how she pulled off this impossible trick. Howe created the coldest substance in the universe, a Bose-Einstein condensate. We're talking just billionths of a degree above absolute zero. At these insane temperatures, atoms stop acting like individual particles. They merge into a single, ghostly quantum wave. Now, when light hits this ultra-cold cloud, something beautiful happens. The light doesn't just get slowed down by thick material. That's not what's going on. Instead, the light pulse gets caught in a quantum handoff with the atoms. Picture this. You're trying to relay a complex message across a room, but instead of shouting it, you have to whisper it to the person next to you. They have to fully understand it, memorize every detail, think about it for a moment, then whisper it perfectly to the next person. That's way slower than just yelling across the room, right? That's exactly what happens to the light. The pulse transfers all its energy and information to the atoms. The atoms hold onto that information in their internal quantum states. Then they release it as brand new light. The original light beam actually disappears. It gets completely absorbed and converted into atomic vibrations. When conditions change, those atoms spit out the stored information as a new light pulse that continues on its journey. When Howe stops light, she's storing the light's information in the atoms, like pausing a video. The light vanishes, converted into quantum memory. Change the conditions, and the atoms release that memory back as light. The pulse picks up exactly where it left off. But here's why Einstein can sleep peacefully. No information actually traveled faster than the universal speed limit. It got stored, then released. Like that message relay where someone holds the message for a while before passing it on. The message didn't teleport, it just took a break. But I promised you could break the speed of light, and you absolutely can. In fact, it happens in your backyard. Ever wonder why nuclear reactors glow blue? It's called Cherenkov radiation, and it's basically a light boom. Remember how light slows down in water to about 225 million meters per second? Well, particles don't have to follow that rule. When cosmic rays slam into our atmosphere, they create particles that dive into water, moving faster than light can travel through that water. When this happens, the particle creates a shockwave of light, that eerie blue glow. The particle is outrunning light in that material, creating a cascade of photons in its wake. It's exactly like how a jet creates a sonic boom when it goes faster than sound, except this is a light boom. This happens constantly. Every time cosmic rays hit the atmosphere above you, particles are breaking the speed of light in air and water. The universe is having light booms all around you. But things get even weirder. In 2000, physicist Li Junhuang created light that seemed to travel backwards in time. He sent a light pulse into a chamber of cesium gas, and the front of the pulse appeared to exit before the entire pulse had finished entering. This sounds like time travel, but it's trickier than that. Imagine you throw a ball at a magic wall. The wall somehow knows what ball you're about to throw, so it throws an identical ball out the other side before your ball has completely hit the wall. The ball that comes out isn't your ball, it's a copy created by the wall's weird properties. That's what Wang's cesium gas did. The material has this bizarre property where it amplifies the leading edge of light pulses while absorbing the trailing edge. So you get a pulse exiting before the original pulse fully enters, but no actual information travels faster than light. The gas is essentially predicting and recreating the pulse, not transmitting the original one. And then there's quantum entanglement, Einstein's spooky action at a distance. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. This connection happens faster than light could travel between them, but you can't use this to send messages. It's like having two magic coins that always land on opposite sides. When yours shows heads, the other always shows tails, instantly, but you can't control which side your coin lands on, so you can't send Morse code. The correlation is instant, but you can't transmit usable information. Why does any of this matter? Because it completely changes how you should think about the universe. First, that cosmic speed limit isn't as absolute as you thought. Space itself can expand faster than light. During the first fraction of a second after the Big Bang, the universe grew faster than light could cross it. The galaxies aren't racing through space faster than light. Space itself is stretching, carrying them along. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move apart, but they're not sliding across the balloon's surface. The surface itself is expanding. Second, the technology coming from this research is going to revolutionize everything. IBM is already building computer chips that manipulate slow light, potentially creating optical computers that process information with light instead of electrons. These could be impossibly fast and efficient. The ability to stop and store light could create optical memory systems that make today's computers look like pocket calculators. Third, these experiments are testing the deepest laws of physics. Scientists are looking for tiny violations of the speed limit that might reveal new physics beyond Einstein's theories. Even the smallest deviation could unlock secrets about how the universe really works at its most fundamental level. And finally, this shows you how science actually progresses. We're not breaking the speed of light, we're discovering that our simple understanding was incomplete. The universe is far stranger than the basic rules we learn in school. Light can crawl slower than a bicycle, race faster than itself in different materials, and appear to arrive before it left. None of this violates the fundamental laws, and it reveals how wonderfully complex those laws really are. So the next time someone tells you nothing can go faster than the speed of light, you'll know the real story. You can tell them about particles creating light booms in swimming pools, about scientists who froze light with the coldest substances in the universe, and about pulses that seem to travel backwards in time. The speed of light isn't a simple speed limit, it's a fundamental feature of reality itself. And understanding how it can be bent, broken, and manipulated reveals just how beautifully weird our universe really is. We're not just breaking the rules, we're discovering what the rules actually are. And trust me, they're way cooler than anyone told you in school.